Today's topic is relative motion, which is going to be relatively straightforward, which is nice, and kind of according to what you understand, which is nice. But eventually, not now, but in the dim distant future of the end of the class, we'll talk about this again, and we'll see how these considerations end up being fundamental, so fundamental that they led Einstein to completely revolutionize what we understood about the world. We live in a different world than we thought we did because of what we're going to study today, and one other implication we're going to push off. So watch this clip from a very early Val Kilmer movie. So what was going on there? What went on there was the idea that we're used to seeing in movies and so on where the train pulls out of the station and we see all the stuff going by, all the trains, the train station, and then the trees and roads and stuff all going by, which indicates to us that the train is moving forward. But for Val Kilmer sitting at that window, he was unable to tell what was actually moving. What was actually moving was, of course, that goofy train station mounted on a truck. The movie itself is one of these really bizarre movies, and it's hard to explain why they would set up that gag, but it's just a sight gag. But the physics of it is fundamental, which is that we can't ever really tell how fast something is quote-unquote really moving. We don't tell how fast it's moving relative to some reference frame. And today is about how do we switch from one reference frame to another. We're going to build our own constructed thing, a little bit contrived. Imagine that Alice and Charlene are in a room that's 10 meters long, and Alice throws a baseball, which Charlene catches half a second later. So, pitcher, and Charlene catches it. And it takes half a second. And the question is, how fast did Alice throw the ball? Don't overthink this. It's a pretty easy calculation, but try and work it out. And of course, it will come down to that the velocity that the ball is moving relative to Alice, we'll use this notation a lot today, is going to be how far it traveled, as measured by Alice, over how long it took. Or 10 meters over half a second. Alice threw it at 20 meters per second. And it really wasn't meant to be deep or hard to think about. That's exactly what we've been talking about for the last 2 weeks. Different problem. Dexter's watching a train go by, and it's moving at 30 meters per second. How many meters does it move in half a second? Well, now we'll say that the distance that Dexter sees is the velocity of the train as measured by Dexter. And again, we'll come back to that notation, times the time. So it's going to be 30 meters per second times the half second, or 15 meters. And again, not surprising, don't overthink it, nothing particularly deep going on here, just doing some calculations like we did in Unit 1. But here is the reveal. Actually, the train that Dexter is watching is the one carrying Alice and Charlene. Thus, from his point of view, the ball has traveled from where Alice was to where Charlene is. And that is more than just the car length. That's more than just the 10 meters of the car. How far is it? Right. So from here, remember, it takes half a second, and then Charlene catches it over there. And we can see that it traveled 25 meters. It went the wall, if you want. Charlene moved, as we said before, 15 meters, but the ball had to cover this distance as well, and that was 10 meters, so the grand total is 25 meters. Really nothing deep going on here, nothing weird, but we've already introduced kind of a weird shift because now the distances are depending on who's measuring them, and that's going to tell us that there's something interesting going on. Just to sew it all together then, what speed does Dexter say the ball has? What would he say its velocity is? In fact, we should probably talk about what velocity does Dexter say the ball has. And here it is as simple as saying the velocity that Dexter sees the ball take is going to be the distance the ball travels according to Dexter. Sorry, that was kind of messed up. Delta x of the ball as measured by Dexter over the time. That was 25 meters over half a second. He sees it traveling at 50 meters per second. So Alice sees it traveling at 20 meters per second, but Dexter sees it as 50 meters per second. And it's not surprising, sort of to lead the eye, that there's a connection between them. This is what's going on. Now we're going to formalize all of that. So we're going to say what happened in the last one. We said that Dexter sees the speed of the ball as being whatever Alice sees, plus however fast Alice is moving. That's how Dexter sees it. And we're going to introduce some formalisms that are moderately complicated. We still have vector stuff, obviously, and we're going to say that we're going to have the velocity of the ball as measured by Alice. And I've been using this notation, but we'll formalize it here. The upper subscript is what you're measuring, and the lower subscript is who's measuring it. And we see that Alice says that there's something going 20 to the right. And then the velocity of Alice, which is the velocity of the train, as measured by Dexter, therefore would be v for velocity, Alice as measured by Dexter. And we know that that should be 30, which means it should be about half again as long as that, and it is. And then finally, the velocity of the ball as measured by Dexter, and that would be VBD. And what we sort of walked through, we haven't proven it, but it seems reasonable, we can see that the 20 of Alice plus the 20 that Alice sees the ball moving plus the 30 that Dexter sees Alice moving becomes the 50 that Dexter sees the ball moving. All right, that VBD is VBA plus VAD. This is called the relative motion equation. Also, there's a thing that goes on here that's worth at least noting, that we can see that there's this subscript where Alice is in the bottom subscript for one thing and she's in the top subscript for the other, and it's almost as if they contract or go away and we just get B and D here. Or if you want to put it differently, if I want to measure, if I want the ball with respect to Dexter, but I want to introduce Alice for some reason, like I have something measured by her, I can sandwich in her here by sort of putting her on each thing. This gets the kind of technical and weird phrase contraction of the indices. That's a fancy term that we use for this, where in essence we combine them, right? We move to Dexter's reference frame by combining these two indices. I will admit that this is a lot of formalism for what was a really simple problem, but the point is that the equation is going to be true whenever there's relative motion, whether it's in the same direction or opposite direction or a complete angle or whatever. And I want you to have one example where you know the answer intuitively, so you can come back and re-justify to yourself what the equation needs to be to give you the result that you know. Now, what if Alice had been throwing against the motion of the train? So she had been throwing backward against the train's motion. Then what would change, of course, is that her arrow would have been flipped. The ball would be moving, if we consider this to be like eastward, then the ball would have been moving westward, so we'd flip the sense of the arrow. But the other two guys would look the same. This, of course, is no longer the correct picture, right? And we should keep that in mind, that these don't add up to each other, so they're wrong. We'll see in a second how it goes. Graphically, then, we would have that the velocity of the ball as measured by Alice plus the velocity of Alice as measured by Dexter gives me the velocity of the ball as measured by Dexter. And we've done this, I guess I swapped them for no particular reason, but we've done this in tip-to-tail notation, VAD plus VBA, and we're left with this guy, which is here. We can see that numerically what we'd have is the same kind of equation, but now we would have had minus 20 meters per second eastward plus the 30 meters per second originally eastward gives us 10 meters per second eastward. It's still moving forward, but not nearly as fast, because essentially the train saps some of its energy, right? So it traps some of its velocity, although that's fuzzy and not a precise physics term. What if Alice had been throwing against the motion of the train, and she happened to be throwing at 30 meters per second? So not the things we've been talking about, but she suddenly gets a burst of speed, burst of strength, and she throws the ball 3 times as fast. So now it's moving 30 meters per second westward when the train is moving 30 meters per second eastward. What would Dexter see? Lucky for us, the Mythbusters a few years ago went and did this to illustrate, and hopefully you have a sense in your head. But what would actually happen is the plus 30 forward would be canceled out by the minus 30 backward, and from Dexter's point of view, the ball would just seem to hang out there, but really it wouldn't hang out there, it would just seem to fall straight downward.
So what are you so excited about?
Well, it's our turn to try a new type of myth, the physics thought experiment.
Great. Something to get the old gray matter working.
So here's how this one goes. Let's say you're driving along in a car at X miles an hour. You throw something out the back in the opposite direction at the same speed. Does it just fall straight down?
Build an air cannon, fire a soccer ball at 60 miles an hour. We'll do it again inside of a moving vehicle going 60 miles an hour. See if the energies cancel each other out, and we get a vertical drop.
Love it. Let's do it.
With the forward and backward momentum matched as close as they're going to get it, the pressure's on Grant for a perfect release.
I don't know about you guys, but that looked pretty good to me. Let's check the high speed.
It really looked good to the naked eye, but the judge in this case is the high speed.
Oh my God, it's like a cartoon. It's just in the air, it stops, and it just falls.
Look at that.
Fantastic.
I mean, look, it doesn't move at all. It's going straight down.
Woo! We did it! We did it! Yeah! Vector edition! Yay! We canceled out velocity.
After 3 days of suffering, that single shot brings the myth to an end.
I can't be happier. We actually got the speed of the car to match the speed of the soccer ball, and we got a perfect straight down drop.
Ladies and gentlemen, the laws of physics are still hard at work.
All right, so there you go. Physics does in fact work even out in the wild, at least sometimes. All right, for the rest of this video, we're just going to walk through some sample cases about how to apply this formula. So Horatio is on a raft drifting downstream at a rate of 2 meters per second, and his walking speed is 4 meters per second. Imogen, on the riverbank, watches Horatio walk along the raft in the downstream direction. With what speed does she see him move? As a note here, walking speed is his speed measured against the thing he's walking on. It's how fast he can propel himself against that surface. So in this case, it's his speed as measured by the raft. So as always, we should probably start with a little picture. So here is the river. Here's Horatio on his raft. Or, well, here's the raft. Here's Horatio walking. And Imogen out here is watching him. Right, she's watching him. And so she sees a velocity of Horatio as measured by Imogen. That's what we want. We want the magnitude of that. The velocity of the raft with respect to the water, well, it's drifting downstream at 2 meters per second. So we'll say something like that. And we have here that the velocity of Horatio relative to whatever he's walking on, which in this case is the raft, is 4 meters per second. And this is the key bit. She sees him walking in the same direction as the raft is going. And almost out of room, unfortunately. So I'm going to switch to a different screen. All right, redoing our picture, we get something like this. And we find that the velocity of Horatio as measured by Imogen is the velocity of, and this is a little weird, but of Horatio as measured by the raft, or really somebody on the raft. And then we want to add in how fast the raft is moving relative to Imogen. So we get that's our vector equation. And again, we know it's the right vector equation because we want to get rid of the raft information. We want to be able to contract those indices. But here it becomes really easy. This is going to be 4 meters per second. Let's do it in the right color. 4 meters per second, and let's say we'll pretend he's moving eastward. And then we add 2 meters per second for the raft, also moving eastward, and we not surprisingly get 6 meters per second in whatever direction the raft had been moving. And again, this is overkill. This is using, a nuclear weapon to kill a fly. It's too much work for what we could have just jumped to, but it's good to get practice with the formalism because the problems are going to get more complicated. New problem. Take plus x to be eastward. At the airport, Bob walks along a people mover, which is a conveyor belt that carries people, that itself moves eastward at 5 meters per second. Eugenia, on the floor by gate 12, sees Bob moving eastward at 8 meters per second. What is Bob's walking speed? In other words, how fast does he walk against the conveyor belt or against the ground when it's not moving or whatever? So let's draw our picture. We have a people mover, and let's just talk about some points on the people mover. We have Eugenia out here watching things, and for some reason timing stuff. We have Bob over here walking. I don't really know which way, so I'm going to just choose that he's walking with the people mover. So we have that. We're told that the people mover, as measured by Eugenia, because she's on the floor, and she sees the same thing as the people mover, and that moves eastward against the floor, or therefore, according to this, also versus Eugenia. Eugenia sees it moving at 5 meters per second. And Eugenia also sees, she sees Bob moving, and he's moving at 8 meters per second. And what we're looking for is, what does Bob move relative to the people mover? So again, this is V of Bob relative to the people mover. And we don't know what that is, but we'd like to know. We'd like to figure it out. All right. So everybody up here. Sorry about this little bar in the middle of the page, but we're kind of stuck with that, and that's where it's going to go. We're going to set up our relative motion equation, and we know that it's going to look something. One thing is the sum of two other things. And what we'd like to do is get rid of the people mover. So we want that in the middle. So we'll say V of Bob and people mover, and then V of people mover relative to Eugenia. And I'm being a little ruthless here, and I'm saying I want to get it so that I have two indices that contract, and when they contract, they will give me Bob relative to Eugenia. So we get something like that. And then we can put in the numbers that we actually know. So, for instance, we know that Bob relative to the people mover, I don't really know what that is. That's what I'm looking for. But I do know that the people mover relative to Eugenia was 5. And I do know in the end that she saw the people mover, or she saw Bob moving at 8. So I get something like this, that 8 meters per second is Bob's speed plus 5 meters per second, which allows us to then, of course, easily solve that Bob's speed relative to the people mover must be 3 meters per second. And this was not that much harder, but was still a little more complicated, and the notation helps us keep track of everybody. New but related problem. Take plus x to be eastward. At the airport, Fergus walks along a people mover that's moving eastward at 5 meters per second, so basically the same people mover. And Eugenia is again seeing at gate 12, and she's seeing Fergus, but she sees him moving westward at 3 meters per second. What is his walking speed? So now we can say, again, if we draw our picture, here's the people mover. Here is Eugenia out here at gate 12. And for whatever reason, bizarrely timing, and we have that the people mover is moving this way, and so she again sees that the people mover is moving relative to her at 5 meters per second. A point on it is getting closer to her at 5 meters per second, say. But now we have Fergus. If Fergus is moving westward, then he must actually be walking westward, because if he were walking eastward, the thing would speed him up a lot. So we'll say this is the velocity of Fergus relative to the people mover, but it's westward. So the arrow takes care of that for us. And then Eugenia sees him moving. That's Fergus relative to Eugenia. And we know that that is also westward, but it's 3 meters per second. So again, let's get some clearance here. And we can say we still have a very similar thing where we want to get rid of the people mover. So we'll have the velocity of Fergus relative to the people mover, and the velocity of the people mover relative to Eugenia, and they will contract to give us the velocity of Fergus relative to Eugenia. And then which of these things do we know? Well, if we stick with our convention, and we don't have to, but let's, then we can say that the velocity of the people mover is 5. That's good. Oh, I should be clear about some of these things. This is a vector equation, and I and you should always be careful that it's a vector equation. So we look up here and we say, let's translate our guys into this. So we have down here definitely the 5 meters per second eastward. But over here we're going to have minus the thing I'm looking for eastward. Why do I do that? Because I want anything on my diagram to be a positive number. So I want to take, in other words, the minus is this arrow. I take this symbol, but I apply the correct arrow. And the plus was this arrow. But I don't write the plus, so it didn't show up earlier. In like fashion, I would take this and say that this is 3 meters per second, but it's minus if I want it to be eastward. Now you might wonder, well, why don't I just say 3 westward? But there's actually a good reason, because now I have east in each thing, and I would be able to cancel out. All right, that the effect here is that I can say this and this and this all cancel, and I'm left with minus 3 meters per second equals minus the thing I'm looking for plus 5. Oops. Let's get our colors right. And again, let's get ourselves a little bit of speed, so goodbye picture. And here I can say that if I, add this to both sides, and I add 3 to both sides, then I end up with that the speed of Fergus relative to the people mover is 8 meters per second. He must be moving westward at 8. He's carried back eastward by 3, and so what she sees is 5, which of course was what we thought. Notice here that the speed, which is what's asked for, is 8. The minus sign isn't in here because speeds are always positive. All right, the relative motion equation holds even when the velocities are not aligned. So far we've been doing one-dimensional people movers or rivers or anything like that, and that's fine. I usually end up calling these river problems, or actually I call them conveyor belt problems, because there's just motion along a line. But it doesn't have to be that way. Consider a river that is 50 meters wide, but is flowing eastward at 2 meters per second. And then consider a boat whose engine moves it through the water at 5 meters per second, meaning if the water weren't moving, then the boat would move at 5 meters per second, or relative to the water that it's in, it's moving 5 meters per second. If the boat heads due north, it does not end up directly acrossward, right? So we go here and we head due north. We don't end up over here, all right? The river carries it downstream some amount. So if we have somebody standing on the shore, they wouldn't see it move this way. They'd see it drift over this way. They would say the velocity is at some angle, to the northeast in this case, and we're going to find that velocity. We have our similar definitions. We're going to have how fast does water move relative to the ground, the riverbank, or the person on the riverbank who's watching this. We have the velocity, and that's given as due east. We have the velocity of the boat pushing against the water, and the boat is heading due north and has some speed that was given. And then we'll want to say, what is the velocity of the boat as measured by the person on the riverbank, by the ground, all right, itself? Where does it seem for that person to actually go, even though it's heading due north? And the equation, well, we still want to contract these indices. We still want to work this way. So we get that VBW, velocity of the boat as measured by the water, plus the velocity of the water relative to the ground, gives me the velocity of the boat relative to the ground, we get this. But now this is a much deeper equation than it was 2 or 3 slides ago, because it's not one-dimensional. The directions can't cancel out because they're not all the same. It is a vector equation, though, so we can set it up as the vector equation. If we put these in tip to tail, then this would be the connection. So if we say the velocity of the boat relative to the water, and we add the velocity of the water relative to the ground, we would have this. And that has to become the final thing. And the lengths of these things have to scale themselves so that that works. Since there's no acceleration in this problem, each displacement equal to its velocity multiplied by the time, which means there's a similar triangle going on here. If we want to know how far downstream the person ends up, which should have been the question, and for some reason didn't ask it earlier, then we can see there's some similar triangle going on, because each of these distances here is the velocity in that direction times the time. And so we see that our 5 meters per second here and 2 meters per second here give us a triangle that's 50 and something, and the something would have to be 20. So this boat ends up 20 meters downstream because of the ratio of its crossing velocity to its downstream velocity. Don't get overly attached to this similarity relation, because it's partly a result of the fact that they're at right angles. All right, different problem. An airplane whose airspeed is 300 kilometers per hour is trying to fly from Alphaville to Beta City, which is due north a distance of 150 kilometers. There's a westerly wind blowing whose strength is 100 kilometers per hour. If the pilot does not account for the wind, how far off will the plane be when it's traveled 150 kilometers north? All right, so what is airspeed? The airspeed is literally the velocity or the speed of the plane relative to the air. So that air is going to be being carried westerly by the wind, carried towards the east by the wind, but we want the plane itself will move against that. So if we have our two cities, if we draw a picture quickly, we have our two cities here, and we know that this distance is 150. But we also know that the plane is going to be blown. It's a westerly wind, so it blows from the west towards the east. So the plane will drift some distance downstream. And what we're asking for is this distance as the plane flies or seems to drift over this way. All right, so let's get some velocities and such defined. Well, we already have sort of one. This is the velocity of the plane relative to the ground, someone who's on the ground actually watching it. There will be the air relative to the ground. And then finally, they tell us something about the velocity of the plane relative to the air. In fact, we know this is 300 kph, and we know that this is 100 kph. And again, we'll have a similar triangle, so we'll always say something like the distance we want is 250 kilometers, and we can say this is the velocity of the air relative to the ground times delta t over the velocity of the plane relative to the air, delta t. So it's going to equal 300, 100 to 300, which means that x would have to be 50 kilometers. Here we aren't explicitly using the actual equation that we've given for the relative motion relation, but we are actually using it because we're setting up this triangle to be similar to that triangle. So it's still in the play, we're just not using it explicitly. All right, let's revisit the river from earlier, the one that's 50 meters wide and flowing due eastward at 2 meters per second. Remember, the boat's engine moves us through the water at 5 meters per second. Okay, the following sentence is grammatically terrible. I don't know what I mean by what is the captain needed. We could say this. Actually, I can fix it. What is the angle needed to land due north of the captain's original position? So what angle does the captain need to steer at so as to land due north? Because now by steering west of north, right? Remember this is north. If we steer west of north as shown, then we will be able to go directly across. and we want to figure out what's the angle we have to steer at west of north. All right, here's our setup again. We have the velocity of the water relative to the ground, and we have the velocity of, right, and that's due east. We have the velocity of the boat relative to the water. This is where the captain steers, right? The captain steers the boat against the water that it's in, and so that's at some angle. We don't know what it is. I'm just going to draw it sketchily. And then we want the boat to seem to move directly across the river. So somebody on the riverbank, i.e. on the ground, will see the boat move due north, because that's where we want it to actually go against the river. Which means when we add these again, we have the velocity of the boat relative to the water plus the velocity of the water relative to the ground, contract the indices, and we get the boat relative to the ground. So if I take the boat going this way, but it's carried downstream this much, it has to give me this. And again, all of these numbers and angles have to arrange themselves so as to give me the functional right triangle that I have here. Then we can just put in our values. We were told that relative to the water, the boat moves at 5. We were told that relative to the ground, the river heads downstream at 2, and so we have this triangle. The definition of the sine is opposite over hypotenuse. How did I know to use sine? Well, I usually try sine first just out of habit, but it doesn't really matter. You just pick a trig function, set it up. If it involves the sides you've got, you're set. If it ends up involving this side that you don't, then it was the wrong trig function, and then pick another trig function and set it up. It won't take very long to get a good intuition for where you should start, but even if you guess wrong, it's only 3 of them you have to try, so it's only about a 30-second thing either way. All right, so we say sine of theta is 2 meters per second over 5 meters per second, or 0.4, and therefore, if I apply the inverse sine function, right, if I have sine of theta is 0.4, to get rid of the sine, I have to take the inverse sine of it. All right, I can't just divide by sine because sine's not a prefactor, it's a function. So I find the function that undoes the function, but then algebra says if I do it on the left, I have to do it on the right. The whole point of the inverse sine function is that inverse sine of the sine of theta is theta. The inverse sine liberates theta from the sine function. And then over here, I have inverse sine of a number, and that's just a thing that you look up in a table or you get a computer to do or something. And apparently if you do this, you'll find that it's 24 degrees. All right, so let's revisit our airplane. Airplane whose airspeed is 300 kilometers per hour is trying to fly from Alphaville to Beta City, which is due north in distance of 150 kilometers. There is a westerly wind blowing whose strength is 100 kilometers per hour. At what angle east of north would the plane have to fly to arrive in City B on a direct route? And here I have to admit that I confused language earlier, because a westerly wind means that it's blowing towards the west, whereas a west wind means coming out of the west, because language is goofy. All right, so in this case we have the airplane railway city, city A, I guess Alphaville, and Beta City. And we know that this distance is 150 kilometers. Is that going to be useful? Not sure. And we know that we have to fly, the airplane has to fly this way at some angle. We can call that the plane relative to the air. And we're told that the air relative to the ground is 100, and it's moving westerly. So we would need, and then of course there would be the velocity of the plane relative to the ground. And we know that the velocity of the plane relative to the ground as a vector is the velocity of the plane relative to the air as a vector plus the velocity of the air with respect to the ground as a vector. So that if I take this thing and add this thing, I should get a due north thing. Why due north? Because we want to take the direct route, the due north route. And we were told we're looking for this angle. We were told that this was 100 kph, and we were told that this is 300 kph. So looking at this function, I might offhand say, well, the sine of the angle is always the opposite over the hypotenuse, which in our problem is 100 kph over 300 kph, or 1/3. If the sine of theta is 1/3, and I apply the inverse sine here to liberate the theta, then I have to apply it here, and I end up with that theta is the inverse sine of 1/3. In a calculator, I find is 19. It's actually 19.47, which is disturbingly far from 19, but to two places it's what we got, and we really don't have a lot of accuracy here, so we probably shouldn't say, we probably should say 20, maybe even something like that. But there we